Hello, and welcome to Lecture 29, where we're going to discuss our second to last topic in our rotation chapter, and that is the topic of rotational kinetic energy. We've talked about Newton's second law in rotation, so it makes sense to move on to talking about rotational energy, specifically rotational kinetic energy. This is going to be a wonderful problem-solving technique that's going to allow us to approach certain problems in a much faster way than if we were finding torques and angular accelerations. Okay, so let's get on to section 8.5. There's no new terms exactly. Really, we should just jump into the formulas and see what they are, because they're all going to be variables we've seen before, but just expressed in a different way. Okay? So first of all, let's start off with rotational work. All right? Now, we could define rotational work as a term, but there's nothing that we could say that wouldn't be expressed in the equation itself. Rotational work is torque times angular displacement. And of course, that's very similar to translational work, which was just force times distance. Right? Because torque is playing the role of force, but here, of course, it's torque. And then this is the displacement, but now it's angular displacement. Notice that the units are the same because the units of torque are Newton meters and the units of radians are nothing. Thus, we have that work is still measured in Newton meters, which of course is also joules. Okay? And we can express that work in terms of power, because power is always defined as work over elapsed time. So we can then replace the work with tau times delta theta, right? And here there's just label all those other terms as well. Tau for torque, and then theta final minus theta initial as angular displacement, which we can also just write as delta theta, because they're the same thing. See, those two. Okay? And of course, elapsed time, and that's going to give us our power. That would be the average power, all right? And then if we want to discuss the instantaneous power, so we can think of this one here as the average power, this one as well, if you know the work value. But if you want the instantaneous value of power at a particular moment in time, I've kind of put all the equations into one row here. The instantaneous power would just be tau times omega. And again, that is in a direct comparison to instantaneous power for translation, which was just force times velocity. Recall? And that came from the same relationship between work and elapsed time. Okay, but here it's tau, torque, times angular velocity. Okay? All right, so there we have a way of dealing with the power output of rotational systems. And what kind of systems have power output? I mean, obviously like a windmill. You can think about turning something like a big flywheel, a big spinning disc. It's doing a certain amount of work, and we can calculate that. Okay? Now, the work energy principle applies to rotational systems just as well as it is to translational systems. It's a universal statement that net work is equal to the change in kinetic energy. All right? So that means that we can then, although we're not going to show all the steps in the derivation, but then we can take that idea and bring then the idea of work into a full-fledged conservation of mechanical energy statement. And that's what I have right here. Okay? And now, first of all, I'm going to zoom in a bit on this. First, we're just going to define kinetic energy, because I want us to understand that up to this point, kinetic energy was just 1/2 mv squared. And that was fine. That was true of any system that's just translating. And we can approximate a lot of systems as purely translational, like even blocks on ramps. 1/2 mv squared, okay? Falling objects, 1/2 mv squared. That was their kinetic energy, okay? Now, if we want to consider the energy of rotation, if we're going to treat something as not a particle and include the fact that it has a moment of inertia, it has mass that rotates about its center, then it has to have a second form of kinetic energy, and that is rotational kinetic energy. So thus, total kinetic energy is the sum of translation and rotation. Now, obviously, the best example of a system that has both translational kinetic energy and rotational kinetic energy is a rolling object. Okay, we've seen rolling before because we looked at it in the context of dealing with it in terms of torques and accelerations. We're going to see rolling again. Okay, other systems that would have both translation and rotation is a block and a pulley, because in the total system, although each object doesn't, but the total system would have a combination of translational and rotational kinetic energy. In that case, with a block and a pulley, you would have, or even 2 blocks and a pulley like an Atwood's machine, you'd have some objects that just have translational energy, the blocks, and then you'd have the pulley, which is fixed in place, so it doesn't have translation, but it does have rotation. So the system as a whole would have a combination of translational and rotational kinetic energy. All right? A yo-yo is basically vertical rolling. So yo-yo would have just that single object would have a combination of translation and rotation, because it very much is the same dynamics as rolling, and it's the same conservation as rolling. It's the same kinetic energy as rolling. Okay? Now, when we actually look at the terms, we should be a little bit more careful now when we think about translational kinetic energy, because it is specific to the reference frame of the ground or the surface or the ramp or whatever it may be, or the yo-yo string. It is the 1/2 times the mass of the object, okay? This is the object that's translating, and then its center of mass, the velocity of its center of mass squared. And this is particularly relevant for rolling objects, because if I was to consider the velocity of the perimeter and square it, I would get the wrong answer. That would not be its translational kinetic energy. The only velocity that you can use for the purpose of translational kinetic energy is the velocity of the center of mass relative to the ground. Okay? Make sure that makes sense to you. Okay? Because that is an important step to not get wrong. Otherwise, these problems are very powerful tools to make solving complex problems simpler. But you have to be careful for potential pitfalls, like using the wrong translational velocity. Okay? Okay, so we're good there. And then the rotational kinetic energy has it's a new expression, but it's very much analogous, and it's going to be 1/2. And then instead of mass, it's the moment of inertia, and it must be the moment of inertia relative to the center of mass, because it has to be relative to the same point that was translating, right? So it's a moment of inertia about the center of mass. So for like a sphere, it'd be 2/5 mr squared, okay? And then it's the angular velocity of the object as a whole. This one you don't have to worry about a particular point, because the whole object has one angular velocity, okay? And so that would be the total kinetic energy of an object that has both translation and rotation, like a rolling object, or a system that has multiple objects, some of which translate and some of which rotate. Furthermore, and an important idea here is that anything that is rolling will always move at a slower rate than if it was sliding. We saw that. We actually arrived at that same finding by using accelerations, and clearly showing that the acceleration of rolling objects, in that case it was a solid sphere and a hoop, were both slower. They both had smaller accelerations, and they had smaller final velocities than an object that would have just be sliding without friction. And that's because the object that slides without friction doesn't have to share any of its kinetic energy with rotation. It can just translate purely. And we're going to see that again in the very last example in this notes in a very interesting way. Okay? A way that I think is very interesting. I hope you do as well. Okay? So translational velocity of the center of mass. I want to say here I just labeled the principle of the work energy. All right? And then this is the rotational kinetic energy, this whole term, the second term. But again, notice how they have the same form. And that's the great thing about rotation, is everything looks the same. You can see, right? like that power equaling tau omega looks an awful lot like power equaling force times velocity. We basically just replace each of the translational terms with the rotational terms, but all the expressions have the same form, right? M is replaced by I. V is replaced by omega. You get it, right? So then if we want to think about total mechanical conservation, the way that we would see that is we would include gravitational potential energy, all right? We're not going to do any systems that include translational kinetic energy, rotational kinetic energy, gravitational potential energy, and elastic potential energy, because that's the one thing that's missing from here. We're just not going to include that in any of our problems. So the most amounts of energy that we would see in our conservations here would be 3 terms on one side and 3 on the other. Furthermore, notice that we're not discussing any non-conservative forces here. It's just kind of for simplicity's sake. We could, especially in a system that had blocks and a pulley, we could rather easily add a non-conservative force to one side, to this side. But to rolling systems, there are some complications that come if we do try to introduce the idea of non-conservative forces, because that whole idea that friction is there but not doing work for a purely rolling system. So we're not going to touch that. So again, what you need to know and what you need to kind of be aware of is that all the energy conservation problems are going to look like this. We're not going to have any extra steps to them. Okay? All right, so let's look at the types of problems that we're going to do for practice, because they were definitely ready to do some practice problems and see what conservation of energy using rotational kinetic energy is all about. All right, and again, let me just say I just have to say this, that this is a wonderful tool. Don't think of this as another burdensome topic to remember. Think of this as an easier way to solve certain problems. Problems that don't ask for acceleration or time or forces can always be solved in a more straightforward manner using conservation of energy. Okay, so that's the great advantage of this approach. So what are the 3 types of problems that we're going to highlight here? Type 1. Problems that involve rotational work and or power calculated with torques and displacements. So these are kind of the odd ones out. These are just going to be using these 2 equations. They're not energy conservation. All right, but I just want to show how torque and energy are connected. All right, then type 2, fairly complex problems that involve objects like pendulums that rotate but do not translate, where gravitational potential energy, the center of mass of the object, can be related to the rotational kinetic energy of the object. So this is an important one. This is important because it can show up in conservation of angular momentum problems, like in the next section. It's important because it can be easily misunderstood in terms of how the energies are related, so I want to call special attention to it. Okay, so we're going to see a couple examples of those, including a couple of concept questions. And then type 3, fairly complex problems that involve rolling objects and or other systems that both rotate and translate, and where gravitational potential energy can be related to both rotation and translational kinetic energies. Okay, and I actually didn't include another example, say, of a pulley and two blocks. It's just to have, kind of save on space. We already saw how to do that with tensions and accelerations, and it's up to you to realize that you can also do it with energy. Instead, I focused on systems where it was more obvious to use energy as the better approach. Again, I want to not do too many examples and stick to the most important ones. Okay, so let's do example 1. A group of people push on a large stone wheel horizontally oriented with an axle through its center and resting on rough ground. The wheel has a radius of 2.5 meters and a mass of 955 kilograms. By pushing with a combined force of 3,275 newtons, the group is able to keep the wheel turning at constant angular velocity. And the wheel makes 3 complete revolutions in 7 minutes. Okay, so think of this as some giant grinding wheel from ancient times, and a big team of people are pushing it around. Okay? Okay, so here's the idea. The work of pushing is equal to the torque times the angular displacement. All right, this is just the definition of a rotational work. Our displacement is going to be 3 times 2 pi, because we were told that it was 3 complete revolutions. So there's our displacement, 6 pi radians. All right. And there we have, then the torque of pushing is the total force of all those combined people. We're not told how many they are. We just care that it's total force. And we're told that they push, we're told that they have a total pushing force. It could have been more specific and said, been very explicit in saying that the force is perpendicular to the radius, or the force is tangential, but we're going to assume it is because it wasn't stated otherwise. All right, so notice then that in the definition of torque, there's no cosine no side of an angle, because we're assuming that the angle between the pushing force and the radius is 90 degrees, which allows for maximum torque. Okay, because then it's sine of 90, which is 1. Okay, so we just put in our total force, multiply by the radius, and there we have our torque, 7,860 newton meters. Okay, so therefore, the total work of pushing over those 3 complete revolutions is going to be the force times the angular displacement, or 1.48 times 10 to the 5th joule, so 148,000 joules. Okay, so that's how much work they do. All right, and they do it in 7 minutes. So now let's see how much work is done by friction. Well, since we were told that work net equals 0, then we can say, oh, well, in that case, friction must be doing just as much work as pushing, since there are no other forces, thus no other torques. So that means that friction is doing negative 148,000 joules. We've seen that idea before. When we have a system which has constant velocity, we can always use the net work equals 0, which of course comes from the work kinetic energy principle. Now finally on to power. All right, we're going to use that value of 7 minutes. All right, so the average power output is just going to be work over time. So we take our work of pushing and then divide by the 7 minutes in seconds, so 7 times 60 seconds. And there we have it. We have an average power output of 353 watts, which may be an instantaneous power output if they really keep up a steady push. All right, so there we have how much total power these people are putting in. Okay, all right, looks good. Okay, let's do another work problem involving rotation. Example 2, how much work would it take to spin a bicycle wheel from rest to an angular velocity of 12 RPM, that's revolutions per minute? The wheel has a radius of 13 centimeters, it has a mass of 4 kilograms, and for the moment of inertia, we're going to use that of a solid cylinder, which is an approximation surely for a wheel, right? They're not quite solid cylinders, but we will use it, 1/2 mr squared. How much constant force would be needed if this acceleration of the wheel was done in 4 rotations, and assume the force is applied perpendicular to the radius of the wheel. So there we're specifically told that we're going to be using that torque is just going to be force times radius. All right? Okay. So here we have the work kinetic energy principle. So work net equals delta K. And here there is indeed a change in kinetic energy because after all, there was a lot of mention of acceleration. Okay. So then the work to spin is just going to be equal to 1/2 I omega squared minus 1/2 I omega naught squared. but the wheel started from rest, so that the initial kinetic energy is 0. So that means that the work to spin up the wheel to that particular rate of 12 RPMs is just equal to the final kinetic energy of the wheel, which makes sense, right? And so then we just have 1/2. Then we're going to insert the moment of inertia as 1/2 mr squared, plugging in the appropriate mass and radius, converted to meters. And then our omega is going to be 12 RPMs. Well, 12 RPMs is 12 revolutions per minute. A revolution is 12 times 2 pi in terms of radians, and a minute is 60 seconds. So what I've done here is just converted 12 RPMs into radians per second, which then would end up being 24 pi over 60 radians per second, and then remember to square it. And there we have our actual work to spin up the wheel, which is 27 millijoules, okay, or 0.027 joules. So not a lot of energy, but it wasn't a very massive wheel, okay? All right, and we want the force, so then in part B, let me just read the problem first. So how much constant force would be needed if this if the acceleration of the wheel was done for 4 rotations, okay? So here we're just going to use the definition of torque, all right? And so we know that torque is Fr, right? That's how we calculate torque. And then we know from Newton's second law, torque is equal to I alpha. All right, and to find alpha, we simply consider the final angular velocity. So this is very much a kind of a throwback to material we've seen before. So we're just going to use the final angular velocity and then solve for alpha. So then we have that, all right? And so then I'm just going to substitute that value in for alpha, all right? And then solve for force. R cancels, so we have a cancellation of one of the R's, although one will be left behind. So then the force ends up being 1/2 times the mass times the radius, and then times omega, which I've calculated here is 1.26 radians per second. That's just this value here. Squared it, and then divided by 2 times the displacement, and 2 times the displacement is going to be 4 revolutions, and so there it is. All right. So then the force ends up being 8.17 times 10 to the negative 3 newtons, or in other words, 8.17 millinewtons. Okay. All right. So we can see how, just like when we did translation, work is very much a bridge from forces to energy. All right, and that's what we see here. We see kind of throwbacks to discussions of torque, which is the rotational analogy of force, and it's kind of, but we're also seeing ideas such as kinetic energy pop up as well. Okay, but now we're going to move on to full-fledged conservation of energy problems. Where we're just going to be setting up the idea of E1 and E2 and seeing what happens between those points. All right, so let's do that. Okay. And hopefully that really does sound familiar, because I hope you remember all those problems that we did in terms of energy conservation, where we said, okay, here's the energy at point 1, here's the energy at point 2, and then we just, made sure the energy is equal to each other and solve for some unknown, which is often velocity, maybe it's displacement. Okay, that's the same idea we're going to be doing here. But before we get there, I want to illustrate a very interesting idea that relates to a pendulum. And a pendulum is such an important system in physics. It captures so many important ideas in terms of at least mechanical physics. Okay? So we're going to discuss 2 types of pendulums. Okay? We're going to discuss simple pendulums, which we've actually seen before. We've even seen in our chapter on translation. How is that? Well, there's a reason. Okay? So let's read the question here. So I want you to show, or I want to show you, that conservation of rotational energy and conservation of rotational energy give the same maximum velocity for a simple pendulum that is released from rest at a given height. It doesn't have to be released from rest. It's just going to be able to a way to illustrate this idea in a simpler way than, say, giving initial velocity. We could give it initial velocity. It wouldn't matter. Okay? And so we're going to have energy conservation from 1 to 2. But here, this is amazing, right? Because this is going to be showing that we can use both approaches for this type of pendulum. Okay? A so-called simple pendulum. We were fine. We weren't breaking any rules when we did it in the translation chapter, because it is a translational system. Okay? But now we can also do it in the rotational chapter if we account for the correct moment of inertia. Okay? Because the moment of inertia, I, of the simple pendulum, is the same as the moment of inertia of a hoop. How the heck is that? They're totally different objects. But not really. Because what the hoop and the simple pendulum have in common is an approximation that all of the mass is some distance away from the center of rotation, the pivot point. Okay? All of the mass, because that was the idea of the simple pendulum. We took the mass as a particle at the end of a massless string. That was always the assumption we made. A hoop, a perfect hoop, is so thin that all of its mass is all the way on the edge. Same idea. Even though here the mass is concentrated, it's still behaving like a hoop in that it's being distributed through motion all the way at the edge. Okay? So that particular simplification of the simple pendulum allows it to be treated as a translational object, but then also work as a rotational object as long as we use this moment of inertia, the moment of inertia that represents an object with all of its mass at the end, okay? Because it's a massless string. Okay, so considering conservation of energy, E1 and E2 using translational energy, all right, we're going to say mgh because that's just the height, okay? And we don't really worry about the center because it's just mgh, and the center is the entire distribution of mass. There is only one point after all, okay? So that's just the release height of h. When it gets down to the bottom of the swing, all that gravitational potential energy has been converted to kinetic energy. That surely look familiar, right? And then when we solve for v, the final translational velocity of the pendulum, it's just square root of 2gh, which is the same exact value would have got if we just dropped something a distance of h, because the path doesn't matter. Gravitational force is conserved. It's path independent, okay? So there we go. We got our value for the final velocity, the velocity at the bottom of the swing, okay? But what if we do it in rotation, okay? I want to show you we get the same thing. So in that case, we consider the center of mass of the system, which has to be just the particle. So it would start at mgh, and then it would be equal to the rotational energy of the system. Why is there only a rotational term? Because from the perspective of considering total kinetic energy as the sum of translation plus rotation, there is no translation here. There's only rotation. And you'll be like, wait, but there is translation. We just did it. Well, that was assuming that rotation doesn't exist. That's assuming that this is entirely a translational system, which we can get away with because it is moving in x and y, okay? And the fact that it's, moving in an arc doesn't matter because translation is still, uniform circular motion is still translation because you can zoom in and look at any point and see displacement in x and y, okay? And that's what we've done here. We've treated it as a translational system. But if we're treating it as a rotational system, is the center, is the pivot moving? Because that's the question you have to ask yourself. If you're treating a system as a rotational system and using total kinetic energy, the sum of translational kinetic energy and rotational kinetic energy, is the pivot moving relative to the reference frame, relative to the ground? And no, the pivot of the pendulum is not. It is fixed in place. Thus, the only form of energy for any pendulum is rotational kinetic energy. Okay? All right? So here we have it. mgh equals 1/2 I omega squared. We're going to use the appropriate moment of inertia for a simple pendulum, which is just ml squared, the same one as a hoop. We're going to replace omega with v over L, and that's because, of course, v equals omega L, so all I've done is just solve for omega. Remember to square it. That allows the L's to cancel out, and then we're just left with 1/2 mv squared. So then we saw was equal to mgh. The m's cancel on both sides. So then when we solve for v, we get the exact same expression. The velocity of the pendulum at the bottom is a square root of 2gh. So it doesn't matter which form we use. The simple pendulum is another bridge of sort in the way that work is a bridge from forces to energy or from torques to rotational energy. Here we have one type of system, one idealized system that can be described with both rotation or translation. And I love that because I think that really kind of allows us to show what our assumptions are, when we're allowed to do something, and now if we look at question 2, when we're not allowed to do something. Because let's now look at a pendulum that isn't the same idealization as a simple pendulum. Let's look at a pendulum that's more like a rod, okay? Like a meter stick pivoting about one end. Well, that is obviously an object. It obviously has a distribution of mass. It isn't all at one point, which means it obviously has a moment of inertia that is different than the moment of inertia of a hoop. That isn't going to give us the same value with translation, okay? So in other words, we want to compare the results of the previous question to something called a physical pendulum, which is a funny name because, of course, physics apply to simple pendulums as well, all right? But think of the physical pendulum as being evocative of the fact that this pendulum is more realistic. Because really, if we were going to treat the simple pendulum as more realistic, we'd have to consider that the mass is at least distributed as a sphere and not as a single point, right? That would help. That would actually give us some variation between it, okay? Or what if we included the mass of the string, right? That would be more physically realistic, right? And so that's what we're doing in this so-called physical pendulum, all right? So the idea here is it has mass m. It has a moment of inertia of 1/3 ml squared. Well, where does that come from? Well, it comes from calculus, of course, but it's the moment of inertia, if you were to look it up in a table, for a rod, a uniform density rod, like a meter stick or a board or something, or just a metal rod, that has, as I said, uniform density, and it's being pivoted about one end. If you pivot it about the middle, it's a 1/12 ml squared, by the way, because of course the pivot point determines the moment of inertia. But if you're rotating a rod about one end, then its moment of inertia is 1/3 ml squared, where L is the entire length. And you can see half of L is illustrated in the figure. Okay, so it has the pivot point shown. And now the question, does the conservation of rotation and translational energy give the same maximum velocity in this case? No, it will not. I'm going to give it away, but let's show that. Okay, so H represents the change in height of the center of mass. Here you have to be more specific about saying that it's the center of mass. All right, we're going to use conservation of energy. Okay, and we're going to use conservation of rotational energy, mgh equals 1/2 I omega squared. All right, and then so that's, because basically the center of mass starts at some height. Just if I'm going to kind of add this here to the figure, this would be like h. All right, because the center of mass right there is going to swing down to some lower point. Okay. All right, so there's the initial gravitational energy. And again, why are we taking the initial gravitational energy at the center of mass? Because that's what you always do. Okay. Anytime you discuss the gravitational potential energy of a system that can rotate, that gravitational potential energy is of one point, and one point only, the center of mass, which not coincidentally is the only point where the gravitational force vector is applied. Okay? All right. So mgh right? And that's going to be equal then to the final rotational energy of the system, which again is just 1/2 omega squared. There's no translation because the pivot is not moving relative to the ground. 1/2 times the moment of inertia, 1/3 ml squared, right? A uniform density rod pivoted about one point. Do the same substitution for omega, right? Replace omega with v over L. Remember to square it, and then simplify things. All right, and this is what we get for the final velocity. Okay, look what it's dependent on. It's dependent on the overall length of the rod. Okay, it is dependent on, let's see. So we have L squared. Why do I have the two different L's here? Because I have, because L is equal to 1 I see. We're doing a substitution. So you see I have two L's. Not quite sure why I set it up that way, but little L, it's fine and all, but little L is the actual distance from the pivot point to the center. So in the figure, it would be like this. That's the lowercase kind of cursive L. And I show here that L is obviously just 1/2 the overall length, because here the moment of inertia is based on the overall length, uppercase L. And so I'm just defining little l as 1/2 L. Okay? So in other words, little l is going to cancel out. So we're going to get rid of it. So we'll rewrite this expression. Okay? So that's all I've done. I'm just saying, so I guess because this is a general statement, this would apply to any rod. Then we could have, say, the distance from the pivot point to the center of mass be some value other than 1/2 L. We could have it be any number. So say we could have a rod where the center of mass is 2/3 the way down. In that case, lowercase cursive L would just be 2/3 big L. So this is a more general statement. So I wanted to include that for sort of utility purposes. But in this example, little l is 1/2 big L. We're going to have to go ahead and go back to the conservation of energy, rewrite it, which allows us to cancel out more things, including completely cancel out L. And then we get our final velocity. All right. And this is the one I really want to highlight here, because this is the final velocity using conservation of rotational energy. And notice what it is. Square root 3/2 gh com. So ignore, don't worry about the com, because that would have been, because this effectively is com as well. But notice, they're not the same. The velocity of the physical pendulum is not the same as the velocity of the simple pendulum. Is it larger or smaller? It's smaller. Okay? The physical pendulum will be moving slower than the simple pendulum. Why? Because it's got to accelerate mass over its entire length. Okay? There's a torque applied here, but that means it's got to deal with the mass up here that isn't experiencing as much torque, and that's harder to rotate. It's also got extra mass over here that is experiencing larger torques, but it's got a whole distribution of mass along the length. And that overall effect of having mass realistically spread out over the length of the pendulum means that it's actually moving slower when it gets to the bottom. Its center is moving slower. And by the way, once we find its velocity of its center of mass, we could then find its angular velocity of it as a total. And it effectively could have just not substituted out omega. We could have just solved for omega and actually got the radians per second of the object as a whole. And then once we had that, we could then have found the translational velocity of any point, like the velocity of the tip or the velocity of a point near the pivot, which would be much smaller, and so on. Okay? So this is just one point, but a very important point on the object, its center of mass. But it's not, again, it's not the same fundamentally. And so that tells us that if we were to use translational energy, which would just be this, because translational energy would give us square root of 2gh, it would be wrong. All right? We have to use rotational energy for this more realistic type of pendulum. And that is part of the beauty of rotational systems, is they allow us to do things in a more real life way. Okay? And that's so valuable. Okay. Let's do one with some numbers here. So we have a physical pendulum. It has a moment of inertia of 1/3 ml squared. It's got a mass of 2.24 kilograms and a length of 1 meter, and a pivot that is shown a distance which is 0.34 meters from the center. So here I put the pivot in a slightly different location. Let's see how we can handle that. All right, and which is the center of mass of the pendulum. Center mass is right there. All right. Then how fast will the end of the pendulum, so not even its center, be traveling when the pendulum is vertical if it is released from an angle of 20 degrees? Okay, so this is kind of what a physical pendulum problem would look like. We're going to use energy to solve it. Okay, so we're going to have energy 0.1 and energy 0.2. This is going to be our height in terms of the conservation of energy. Okay, and here we can see the right triangle formed by the distance x from the pivot to the center of mass, and then that value there, which would then, this is essentially going to allow us to calculate for h-com using theta, because we were given theta, not h-com. Okay, so here we have these conservation of energy. It's a simple setup. It's just a matter of then making sure that you have all the terms expressed correctly, like the correct value of h-com and so on. Okay, so it's just mg h-com equals 1/2 I omega squared. All right, and then to find h-com, we just use the right triangle shown here. All right, and then solve for it. So then the center of mass is x, distance from the pivot to the center, times 1 minus cosine theta. Okay, and then we'll substitute that in for h-com. Okay, because now these are all known values. We know x and we know theta. Okay, we cancel out m because we rewrite the moment of inertia as 1/3 ml squared. Okay, and then we're going to go ahead and solve for omega. Okay, and again, we're just using this moment of inertia. We're using it kind of as an approximation, but it works. It was stated in the problem, so it's the one we're going to use. Okay, and so then we're just going to go ahead and solve for omega. All I've done is just isolate it. I did things like combine the 1/2 and the 1/3. All right, which is where the 6 came from. Plug in our numbers, and there we go. We have an angular velocity. Notice I didn't replace omega with v over r. I just found the angular velocity. And the reason is because we were asked for the translational velocity of the tip of the pendulum, this point right here. Well, it makes sense in that case to find the angular velocity of the pendulum as a whole, and then just relate that to a particular point, the tip in this case. So there is the angular velocity of the pendulum as a whole, 1.1 radians per second. All right, and that means that the velocity of the end, that would be this velocity right here, is just that angular velocity times this distance r, lowercase r, and that would just be x plus half the length of the pendulum, okay? Because it would just be this distance, see? X, and then this is 1/2 f, okay? And so when we plug in all the appropriate numbers, there we have it. We have a translational velocity of the tip at the bottom, which is its maximum velocity, because that's the point at which all the potential energy has become kinetic energy, and moving at about a meter per second, or 0.922 meters per second. Okay, so hopefully this approach makes sense. Key ideas here, relating translation to rotation and using conservation of energy, okay, as well as the appropriate geometry in order to relate theta to h. Okay, all right, there we go. Let's do a different system, a rudimentary attempt at a yo-yo. In this case, just a simple cylinder with a string wound around it. We are given the mass of the yo-yo. It's released from rest at a certain height. And then we want to know how fast is it going when it hits the ground. And we're asked for velocity here, not angular velocity, so we're just going to find the translational velocity of its center. All right, so we're going to relate E1 and E2. Now, this is a problem. I didn't change my wording here. I used to have a part B and part C where I asked for the tension as well as the angular acceleration. But we've already done that quite a bit in the previous lecture, so I decided to skip that step for the sake of just kind of focusing on the key material. So we're actually not going to do problem solving approach 3, but we easily could. You could easily find the tension and the angular acceleration. So keep it in mind, but we won't do it here. We're just going to do steps 1 and 2. Use conservation of energy to find the velocity of the yo-yo, and then actually, never mind, we're just going to do step 1 because we don't need the torque. So that's the thing. Conservation of energy is going to give us velocity, and that saves us a lot of work. So we don't need the torques, and we don't need the angular acceleration. Okay? All right, so we're just going to use conservation of energy. All right, that's going to be mgh equals 1/2 mv com squared plus 1/2 I omega squared. Because here we have essentially a rolling system, right? You can even see by the color here. This is a type 3 problem because yo-yos are like vertical rolling, all right? All right, good. And note, yep, is essentially vertical rolling. So and also the velocity of the center of mass is just omega r, okay? And that's just based on the fact that the velocity relative to the string here is a distance of r. So, and again, remember this applies to rolling because this is an idea I discussed in the last lecture, and it's very much a relative velocity idea because if the velocity of the perimeter is omega r relative to the center, relative to COM, then the velocity of the COM relative to the ground must also be omega r. Okay? And so I won't go over the derivation again. I've already done it twice in the last lecture, but here's the idea that applies and allows us to say that the velocity of the center of mass, the translational velocity of the center of mass, is the angular velocity times the radius. All right? True for all rolling objects, including vertical rolling yo-yos. Okay, so then we just have the conservation of energy using the initial gravitational potential energy. That's then going to get entirely used up by the time it hits the ground. When it hits the ground, it's just going to have a combination of translational kinetic energy and rotational kinetic energy. We're going to use the moment of inertia for a cylinder, 1/2 mr squared. If this was a test problem, I'd be very clear to state it. Sometimes in the examples, I'm just assuming that I'm going to use the most reasonable one, in this case 1/2 mr squared. All right. And I've definitely done the substitution here to replace omega. That means I just have a single unknown, which is v, and I just go ahead and simplify things and then solve for v. And there we get a nice result. It ends up being 4/3 GH. And again, remember that this is less than if we just dropped it. If we had just cut the string and let the cylinder fall like a particle, then what would its velocity have been when it hits the ground? It would have been square root of 2GH. All right, we get that from kinematics or conservation of energy. Well, the square root of 4/3 GH is smaller. Of course it's smaller because it can't be translating as quickly because it had to use up some of that potential energy to rotate, which means its translation will always be less than if it was just purely translating without rolling. All right, and if we plug in the numbers, it ends up being 3.13 meters per second. All right, so that is the velocity of the center of mass relative to the ground at the moment that the yo-yo hits the ground. All right. All right, let's do our last two, okay? These are the slightly more complex ones, but I think they're quite interesting. All right, so hoop and a solid cylinder, both with mass m equals 1 kilogram and radius 10 centimeters, start rolling without slipping down an incline of an angle of 31 degrees and a height of 2.4 meters. And I replaced it with lowercase h because that's what I use in the solution. Okay, what initial velocity would the hoop need in order to reach the bottom at the same speed as the cylinder? So in the original printed version, I had time. That is a version of this problem that I've asked plenty of times. But time requires, of course, using an approach other than energy. Time requires using the angular acceleration. And if you want to see a system involving rolling objects and the torque created by gravity, refer to the lecture on rotational dynamics. It's definitely there, okay? But here we want to take a different approach, so we're asking a different question. And I forgot to change the word from time to speed. And speed is what I care about, all right? So again, just to paraphrase, the hoop is going to move more slowly because it has a greater moment of inertia. So if they both were released from rest, the hoop would arrive at the bottom later, okay, and would arrive at the bottom slower. So the cylinder would both get to the bottom sooner and be moving faster when it got there, okay? That's important. Now the idea here is we don't want them to arrive at the same time, but which would be we could do that by giving the hoop a certain initial velocity, but instead we want them to arrive with the same velocity, okay? So they may still have different accelerations, they may still arrive at different times, we don't care. We only want to make sure they arrive with the same velocity at the bottom. So even if the cylinder gets there first and the hoop gets there second, they're still going to reach, when they reach there, they're going to be arriving at the same speed. And you might say, well, how's that possible for them to have the same speed but arrive at different times? Because they could have different accelerations, okay? But that we don't care. We only care about them having the same speed at the bottom because we can then find that using conservation of energy, all right? Okay, so we're going to consider point 1 and point 2. All right, we're just going to, they're both rolling objects, and we're just going to relate the energy from point 1 to point 2 in both cases. For the hoop, we're going to have mgh, and then since we're giving the hoop some initial kinetic energy, the hoop is going to start at point 1 with some initial both rotation and translation. And because it can't have just one or the other. There's no way, since this is rolling without slipping, if it's moving, it must have translational kinetic energy and rotational kinetic energy. Okay? And then we have at the bottom, it's got no more gravitational energy because it's used it all up. And so at the bottom, it just has entirely kinetic energy, both translation and rotation. All right? For the cylinder, it starts with all potential energy because it starts from rest. And then at the bottom, it's got all kinetic energy. Okay? And notice that we have IH for the moment of inertia of the hoop and IC for the moment of inertia of the cylinder. Okay? Next step, all right? Note that the translational velocities are those of the center of mass. That's important, okay? We shouldn't forget that, but here we don't need to call special attention to it. And so from energy conservation for the cylinder, we have, so I'm just going to use this equation here. I'm just going to solve for the velocity of the cylinder, all right? So notice what I do. All right, so I write out the expression, just I'm rewriting this. Basically all I'm doing here is I'm replacing the moment of inertia of the cylinder with the actual expression, 1/2 mr squared, which you get from a table, and I'm replacing omega with v over r. That means that I have a lot of cancellations. M cancels from all three terms, and then r cancels because of it being in the numerator and the denominator here. They're both r squared. So then this is going to simplify to simply gh equals v squared. Why v squared? Well, because we've got, let's see. Well, actually, this should be this should be 3/4. Because I know that's not, yeah. I'm not sure why I left out the 3/4 here. I'll add it and re-upload the notes. Because you can see here, here's the correct answer. It should be the square root of 4/3 times gh. And why 3/4? Well, because you have a 1/2 v squared here, and then you got a 1/4 v squared here, because it's 1/2 times 1/2. And so then 1/2 plus 1/4 is 3/4. So it should be 3/4 right there. And then when you cross multiply, it becomes 4/3 times gh, and then you take the square root of both sides. Okay? And so there you have that the velocity of the cylinder at the bottom is the square root of 4/3 gh, again, smaller than the velocity of a block, which would have a final velocity of just 2 gh. I keep wanting to compare it to the translational system just to give you that perspective, but I'll stop if it's getting old, okay? All right, so there we have, that's the final velocity of the cylinder. Now, why did I do that first? Well, because now, since I know I want the hoop to have that velocity, I can just plug that expression in to the final velocity of the hoop, and I'm done, all right? So let's do that. All right, so I'm going to substitute this into the hoop energy equation, this one here. Okay, and then that will allow me to solve for V naught. So how do I do that? Okay, so then I'm going to rewrite the hoop energy equation. We've got, it's going to have 2 halves. Let's do that. Okay, so this is the initial part, the initial gravitational energy and the initial velocity of the hoop, because after all, that's what we're going to solve for. We're going to solve for V naught. Okay, and then I'm replacing the final velocity of the hoop with what I found from the cylinder energy equation. So I replace the V with the square root of 4/3 times gh, but I'm going to square it, so the square root's going to cancel out. And then the same thing over here, I take the final angular velocity of the hoop and first of all change that to v over r, okay? That way everything's in terms of v, and then I replace the v with the expression from the cylinder. And the last step is I replace the moment of inertia of the hoop with just mr squared, which is the moment of inertia of a hoop and the moment of inertia of a simple pendulum, because it's an E system where all the mass is along the edge. Okay, so it looks ugly, but it cleans up very nicely because all the m's cancel out, and we're going to be able to combine things together. There's a lot of like terms, in other words. So then I end up with just a v naught squared because I have a 1/2 plus 1/2, so it just becomes a 1. And then I have, let's see, so then I have the plus gh, so this should be plus. All right, another little typo there, and it shows up correct on the next line, but I don't want to be confusing, so I'll fix this on the upload. So this should be plus gh because obviously it's positive. All right, and then everything going on the right hand side, well, there's a 1/2, and then just the 4/3 because the square root has canceled with the square, so there's a 4/3 in the gh. All right, and over here there's a 1/2 and another 4/3. Okay, all right, and so we're just going to take those two together. Obviously, it's just going to become 4/3. All right, so then we have v naught squared equals 4/3 gh minus gh. And again, that's because that was positive, so when I subtract it from both sides, it's minus gh. And then you go ahead and solve for v naught, and it's the square root of 1/3 gh. That's the initial velocity that the hoop needs in order to reach the bottom at the same speed as the cylinder, because otherwise it would be slower because it has a greater moment of inertia, which means it's more sluggish, which means it accelerates slower, which means that by the time it gets to the bottom, it would have less energy, okay? All right, so there we go. And the actual number is 2.8 meters per second. And look what it's dependent on. It wasn't dependent on mass. I could have just not given you the mass. Was it dependent on radius? No. Was it dependent on the angle? No. It was only dependent on the height. Okay? And that does make sense because gravity is this conserved force, the path doesn't matter, and it also doesn't matter what the shape is, because a really large hoop would, not make many revolutions by the time we got to the bottom, but would still behave the same. We saw this with acceleration. The acceleration was only dependent on the distribution of mass, the shape. So the shape is dominant here. It's the thing that matters. The actual radius and mass don't matter for these systems. Okay? All right, last example. And this one is particularly fascinating and counterintuitive, but I think it's so valuable to see how it works. So a ball with moment of inertia of 0.033 kilogram meters squared and a mass of 0.3 kilograms rolls without slipping into a bowl as shown. The bowl has friction on the right side and no friction on the left side. Thus, the sphere suddenly starts rolling, or stops rolling, and starts slipping at the low point. So essentially, the ball is rolling perfectly along here, rolling along, and it gets to the bottom, and then suddenly there's no friction at all. So then it just starts behaving like a sliding block, and then just slides up the other side. Okay? And it completely stops rolling. It loses all of its rotational kinetic energy at this point right here. Okay? So if the sphere is released from a height of y equals 1.1 meters on the side with friction, then to what height y2 will the ball slide with no friction on the other side? And notice here the figure already is implying that y2 is going to be less than y. It won't make it up as high. How is that possible? How is it that when it starts slipping, it doesn't make it as high? Especially since we made a big deal about talking how slipping objects are always the fastest if you had a race between sliding things, right? If I included a block as a third object and let it go down, it would be fastest when it got to the bottom, and it would get there first. All right? Well, there's a reason. And let's go through the steps and then justify them with a quick statement. Okay? So how do we set this up? Well, it's going to be conservation of energy. There's going to be 3 points. So conservation of energy between point 1, where it's released, point 2, where it transitions from pure rolling to pure slipping, and then point 3, when it's got nothing but gravitational potential energy left. All right? So first use conservation energy between points 1 and 2. All right? So this is the mgy plus 1/2 mv squared plus 1/2 I omega squared. I probably don't need to say that this is the velocity of the center of the mass, but I will anyway. All right? And so then this is mgy, and then all we're going to do is replace the moment of inertia with that of a sphere, which is 2/5 mr squared, replace omega with v over r. All right? See, it's always the same steps. Okay, then that simply allows us to solve for v, clean things up a bit, and there we go. There's our final velocity at point 2. Okay, now we want to use that velocity at 2 to find the final height. So we're going to use conservation of energy between 2 and 3. So here's the idea. Now at 2, remember we had a certain velocity, and at 2 before, we had a combination of translational kinetic energy and rotational kinetic energy. But at some point, that rotational energy just suddenly disappears because there's a sudden transition from friction to no friction. So when I start at 2 and compare it to 3, I'm just going to start with the kinetic energy because the rotational energy is lost to us. We can't use it. We can't then convert that rotational energy back to gravitational energy because it's no longer available because the absence of friction has taken it out of the system. All right? And so then we're going to take the velocity that we found, plug it in for our initial velocity at 2, and then have it roll up the hill to some height gh, all right? And I've preemptively canceled out the m here. And so then when I solve for y2, it is only 5/7 of y. So indeed it is lower, okay? It's lower because we lost that rotational kinetic energy, and we couldn't use that rotational kinetic energy. We couldn't use all the joules that are included in this term to convert back to gravity, all right? Thus, the height that it rolls up to, or slides up to, on the frictionless slide will be lower than the height it was released at on the side with friction that allowed for rolling. What if we go the other way? All right? Because hopefully that kind of makes sense, seems believable. What if we release the ball at point 3, have it slide, then start rolling, and then roll up to a certain height? Okay? Will it roll higher than when it started? That can't be right. Okay, so this time we start on the frictionless side at y2, all right? And so we're going to use conservation of energy between 3 and 2. So we just have gravitational potential energy just becoming translational energy because there's no rolling going from points 3 to point 2. And so then the final velocity at the bottom is just the square root of 2gy y, just would be true for any sliding object, okay? All right, and then we're going to use conservation of energy, go from 2 to 1. And then when we start at the bottom, we have, remember, if we're going to be transitioning from no friction to friction, that means the ball would suddenly start rolling at this transition if it's going this way from left to right. Okay, fine. If it suddenly starts rolling, then we're going to use its translational velocity to find its kinetic, or its translational kinetic energy, but we're also going to use this translational velocity to find its rotational kinetic energy using v over r to replace omega, as we basically do most of the time. And then we're going to relate that to some final gravitational potential energy, mgy. Okay, looks good. All right, let's then simplify things, cancel out terms, clean it up a bit. Okay, so when we do that, this is just rewriting it. Okay, and then when we finally solve for y, we get that 7/5. It's the reciprocal. It actually goes to a larger height, because if it here I defined y2 as 0.5, here it was 0.79, so they're different heights. But if we release it from 0.5, then it would get up to 0.7. But the thing that's besides numbers, just symbolically, we can clearly see that if we release it from the side of friction, then it gets up on the frictionless side to 5/7 its release height. If we release it from the frictionless side, it will roll up on the side with friction to a height that is 7/5 its release height. It will actually go higher than it started. And that seems impossible. How can you have something roll and roll up to a higher point than it started? Where did that extra energy come from? Well, it came from the stored gravitational energy of the object itself. Because if you think about it, that object, and this very much relates to the kind of the torque explanation of rolling motion, that has some center of mass, and that center of mass has potential energy relative to the ground. If you tip this over and then that center of mass starts to fall, now you're actually accessing that stored gravitational potential energy. And that's what's happened here. That's why when it slid down and then suddenly started rolling, it suddenly allowed us to access that stored potential energy inside the object itself, thus allowing the object as a whole to get to a greater height. Okay? But it sure is interesting, and it's not what you would have expected had you not approached it with the careful tools that conservation of energy allows us. Okay? Well, I hope this lecture has been interesting and informative, and thank you so much for watching.